Welcome to this mini course on causal inference. In the next 7 minutes, we'll walk through what causal inference is, how it differs from correlation, and how we can use tools like propensity score matching and inverse probability weighting to estimate causal effects in real-world scenarios. This mini lesson was a collaborative effort. Cecil and I both contributed to its design. We're colleagues at AT&T working in marketing analytics with a shared background in applied machine learning. This course is intended for learners with a background in math, engineering, or computer science and assumes experience with Python and statistics. By the end of this lesson, you'll be able to describe what causal inference is, when to use methods like propensity score matching or inverse probability weighting, and how to address post-treatment imbalance. We'll also look at a real-world case study to show these ideas in action. Let's get to what exactly is causal inference. Causal inference aims to uncover cause and effect relationships, not just patterns. It's used in the fields of marketing, medicine, and economics. A major challenge is distinguishing treatment effects from other factors like age or behavior. That's where randomized controlled trials come in. Those are the gold standard of causal inference. Random assignment helps isolate the treatment effect by balancing both known and unknown confounders. Machine learning models are great at detecting patterns and associations, but they don't explain why something happens. That's where causal inference helps us go deeper by estimating the effect of interventions. Here's a classic example. Ice cream sales and crime rates often rise together, but one doesn't cause the other. The true driver is temperature. More people are outside in the summer, both eating ice cream and committing crimes. This is a textbook case of spurious correlation, and in observational data, hidden bias can sneak in. That's why we need methods beyond pure prediction to understand effects. In the 1920s, R.A. Fisher introduced randomization in experiments. By randomly assigning participants to treatment or control groups, we reduce bias and ensure the groups are comparable. This lets us isolate the treatment effect, the only systemic difference between the groups. There are 4 key concepts to keep in mind. Treatment or intervention is the action we're studying. The outcome is what we measure. Confounders affect both. And counterfactuals represent what could have happened under a different treatment. Since we can't observe both outcomes for the same person, we use methods to estimate average treatment effects across groups. Randomized controlled trials are powerful, but not always practical. It's unethical to assign harmful treatments, and in business settings, randomized controlled trials can be costly, slow, or easily disrupted by operational noise. That's where quasi-experiments come in. Methods like propensity score matching and inverse probability weighting help us estimate causal effects when we can't randomize. Before applying those tools, let's revisit quickly the basics of supervised machine learning. Supervised machine learning trains a model to predict an output or label based on an input feature. It learns from labeled examples like emails marked as spam or not. The model learns a function that maps inputs to outputs. For example, predicting whether an image shows a cat or a dog. While machine learning finds strong predictors, it doesn't explain the mechanisms behind those predictions. For causal questions, we need more than correlation. Propensity scores help with that. We train a model to estimate the probability of treatment based on confounders. The model's output becomes the propensity score. Inverse probability weighting uses these scores to reweight the data. This creates a synthetic population where treatment is independent of confounders, approximating randomization. Treated units are weighted by 1 over their propensity score. Untreated units are weighted by 1 over 1 minus their propensity score. This adjustment helps balance the groups. Both methods rely on observed confounders and correct model specification. Neither can account for unmeasured variables, and both are sensitive to how well the propensity model performs. To check if we've balanced covariates, we use Cohen's d, a standardized difference between group means. Smaller values suggest better balance. We calculate it by dividing the difference in group means by the pooled standard deviations. Values under 0.1 typically indicate good balance. Once weights are applied, we estimate the average treatment effect by computing the weighted outcomes for each group and taking their difference. Let's apply these ideas to a marketing case study. We tested whether the type of discount offered affects customer retention. Customers were assigned to test or control arms using stratified randomization, but they had to call in to receive the offer, and not all of them did, which introduced bias. We detected this imbalance using post-treatment propensity scores and Cohen's d, then corrected it using inverse probability weighting. The adjusted results gave us a clearer picture of the treatment effect. Now let's talk about some common pitfalls with propensity score matching and inverse probability weighting, and how to avoid them. With propensity score matching, poor matching can lead to bias. To improve match quality, make sure units are only matched when their scores are reasonably close, and always check balance after matching. Matching may also reduce your sample size, so consider matching with replacement. For inverse probability weighting, extreme weights can make estimates unstable. Stabilizing or trimming weights helps. Also, make sure your propensity model is flexible enough. Finally, restrict analysis to areas with good overlap. To wrap up, we explored causal inference, machine learning, and techniques like propensity score matching and inverse probability weighting for estimating treatment effects. We saw how to apply these ideas to real-world data and how to handle common challenges. Check your understanding of this topic by answering the following 4 questions. If you have a copy of the deck, the answers are provided on the next slide. If you missed any, we'd invite you to rewatch this short video to find the answer. If you got them all, then we invite you to join us on the journey of causal inference by signing up for our complete library of videos on the subject. As a parting gift, we provided a link to the seminal paper on propensity score matching as a PDF at no cost to you. That's all for now.